Okay, welcome back to this 12th lecture to this class. So we're basically halfway through, and today I'll do something different than usual. I'll do something that you could call like geometry even, because I'm going to give a very quick introduction to vector bundles. I don't know the background of everyone. I expect some of you might have seen this material before. I hope it's not to be too boring for you. But just to be sure, I wanted to give a very quick introduction to this material because we're going to use it next Thursday. And yeah, I'll black box a couple of properties of paracompact Hausdorff spaces. There is actually a proof in the notes that are online now, if you're really curious. But yeah, I don't think it's very useful. So, okay, let's go with the main definition. So now let X be a topological space. So it's not an element of the infinity category of spaces here. We are actually an honest to God topological space. A vector bundle on X is a triple of ES mu, where P from E to X is a map of topological spaces. S from the fiber product of E itself to E is and mu from C times E into E are continuous maps over X. So these are maps of spaces over X such that it satisfies the following property. For every little x point of X, there exists U, a neighborhood of X, and and V, a complex vector space, and then homeomorphism P inverse of U homomorphism to X times V over X. So that the map to X is the projection on the first component under this isomorphism, such that under this identification, what we need, S of X V W is X of V plus W, and mu of lambda X V is X lambda V. Oh, sorry, let me add a finite dimensional complex vector space here. And I see V as a topological space with the standard topology that complex vector spaces have. So in particular, each fiber EX is given a finite dimensional C vector space structure by S and mu. Okay, so this definition might be different from the one you're used to see. You might have seen definition by giving an atlas of charts and they're required to be compatible in some way, etc., etc. This is equivalent to this. I just prefer to give the structure explicitly. In this case, it's given by S and mu, and then you just ask some kind of local triviality. Oh, and these U are called, typically, these are called trivialization of E. Okay. This shouldn't be surprising. If you've seen the definition of covering space, and I know you've seen it, it's very similar. So, okay. And we're going to concentrate mainly for vector spaces, vector bundles when X is a paracompact Hausdorff topological space. For example, CW complex. In fact, we're only going to care about CW complexes as bases, but and these are technically complex vector bundles. You can give the analog definition of real vector bundles. You can probably imagine how it goes. So I'm going to need this lemma about general topology, which I wrote a proof. It's on the notes, but I'm not going to prove it now. So if X is a paracompact Hausdorff topological space, and if you don't know what these words mean, well, what paracompact means, just take this lemma as one of the two properties of paracompact Hausdorff topological space that we're going to use. Then for every UI open covering, there exists a countable open covering Vn such that each Vn is the disjoint union of Vni with Vni open subset of UI. The Vni's are disjoint. That's very important. So that's fairly easy to prove using the following fact that I'm also not going to prove. If X is a paracompact Hausdorff topological space, in fact, you can take this as a definition of this second property. You can take it as a definition of paracompact Hausdorff for any UI open covering. There exists psi I partition of unity. Subordinate to the covering. So I don't know if you've seen partitions of unity before, but what does it mean? i.e., for every x in not in UI, psi I of x is 0. Oh, sorry, psi I are continuous functions from x to the closed interval 0, 1. So for every x not in UI, psi I of x is 0. For any x in x, only finitely, sorry, there exists V, a neighborhood of x such that the number of functions non-zero in the neighborhood is finite. So in the neighborhood, only finitely many of these psi I are non-zero. And what was that? Oh yeah, partitions of unity. So the sum of the psi I, which makes sense because in every point is a neighborhood where it's only a finite sum, is 1. That's called a partition of unity. And this, in fact, this is completely characterized. A space is paracompact Hausdorff if and only if it has this property. And that's what people normally want to use. And using this property, there is a very short proof of the lemma above, which I'm not going to give you, though. But is this clear, this topological situation clear? As a corollary, if PE to X is a vector bundle, and X is paracompact Hausdorff, then there exists Vn, a countable cover of trivialization. Because you can find an open cover such that E is trivialized over every cover, but then you can apply this lemma here and find such a countable open cover, and you can, well, if you have a trivialization on each disjoint connected component of your Vn, you can build them together to a trivialization. Okay. Oh, I didn't tell you what a map of vector bundles is. But okay, one step at a time. So, questions so far? This was a lot of general topology to drop in your lap, but Okay. So where do I want to go? Okay, yeah. So okay, a map of vector bundles is just a map E prime over X respecting the vector space structure. That is S of F times F is F composed with S, and how do I want to say it? Mu of lambda F is F composed with mu lambda blank. You know it, F of the sum is the sum of the F's and multiplication by a scalar. If you want it, another way of saying is that it's F is a C-linear map when restricted to each fiber. Okay, and we will write pi 0 vect C, vect X for the set of isoclasses of vector bundles on X. And it's pi 0 because secretly there will be a space of vector bundles whose pi 0 is the set of isoclasses. But for now, it's just notation. More generally, the rank of a vector bundle e to x is the function that goes from x to the non-negative integers, sending x to the dimension over c of ex. And in fact, this is locally constant, as it's obvious from the definition of a vector bundle, because on every point is a neighborhood where the isotype of the fiber is the same. So in fact, I will care only vector bundles of constant rank, but just to be clear. And okay, and we write pi 0 vect d side vect x for the subset of vector bundles of rank d. Okay, I think I'm going quite fast, so maybe I should stop for a second. See if anyone has questions. And when I say rank d, I mean the rank is the constant function d. Okay, so let me state the main theorem of today, which we're going to prove in 2 steps. Let X be a paracompact Hausdorff space. We'll write that there is a natural bijection between pi 0 vect dx and homotopy classes of maps from X to BUD, where UD is the group of D by D, sorry, is the topological group. D by D unitary matrices. I think you should all know what a unitary matrix is. Maybe it was a long time ago that you saw the definition, but a matrix whose inverse it's Hermitian transpose. Or if you want, a matrix that respects the standard metric on C to the D. And well, bolstered by this theorem, we will actually define vect dx as the mapping space. And it turns out you can actually give a more intrinsic definition of this space as the coherent nerve of a cannon-reached groupoid of vector bundles and it turns out to be equivalent to this, and it's going to be an exercise, but I'm not going to prove it for now because I want to limit the technicalities, and this theorem is all we need. But I mean, this definition is not completely crazy. Okay. Is it clear what am I aiming to prove for today? Have you ever seen this result before? No? Okay, good. So I'm not telling you old stuff. It's a special case of a more general result. I think Pavel is going to hint at the more general result in the exercise session. But yeah, we are going to only do that. Oh, and I didn't say it, but all CW complexes are paracompact Hausdorff. So in fact, we're only going to care about, in particular, all geometric realizations of simplicial sets are going to be paracompact Hausdorff. So paracompact Hausdorff is very, very general. I think every metrizable space is paracompact Hausdorff. You have to hunt a bit to find a space that's not paracompact Hausdorff. Every manifold is paracompact Hausdorff. Well, by definition, actually, it's part of the hypothesis of a manifold. Okay, is it clear? Can we start? So the first thing that we notice is that the right-hand side is manifestly homotopy invariant, because the left-hand side had better be also homotopy invariant, and that's the first result I'm going to prove. So proposition, let e to x times times 0, 1, let's say, the interval 0, 1 be a vector bundle. Then there exists. Then if we let, e prime to be e restricted to x times 0, there's an isomorphism of vector bundles e prime times 0, 1 as a vector bundle over x times 0, 1. So this is, as a corollary, the isomorphism classes of vector bundles. Pi 0 vect blank is homotopy invariant. And how do you prove it? Well, proof. Suppose you have I want to say is homotopy invariant. Oh yeah. I want to say that suppose if I have fg from x to y maps. I didn't define the factoriality though. So actually before that, let me say, if I have f from x to y continuous map and e to y vector bundle, f upper star e, which is just e times y over x, the pullback is a vector bundle. With the obvious choices of S and nu. I mean, this doesn't change the fibers, so the C-linear structure on the fiber is going to be the same. And that's, well, okay, you can see it as an exercise, but it's really easy. The preimage of every trivialization in Y is a trivialization on X. So, okay, so suppose we have maps that are homotopic. We want to show f upper star of E is isomorphic to, G upper star of E for every E. That is what it means to be homotopy invariant. Well, okay, let H from 0, 1 into Y the homotopy. Have a homotopy. Then H upper star of E is a vector bundle. And so, and h upper star of e restricted to x times 0 is exactly f upper star of e. And h upper star of e restricted to x times 1 is g upper star of e. But by the proposition, they need to be isomorphic, because E is the same thing as f upper star of E times 0, 1, and then its fiber over 1 is obviously the same as f upper star of E.
Could you maybe explain explicitly what you mean by vector bundle times interval?
Yeah, sorry. Actually, what I mean is, well, I mean both literally. So if I have a vector bundle E prime over X, I can just take E prime times 0, 1 over X times 0, 1, and that's a map. And okay, I haven't defined you what the S you write, but the point is that E prime times 0, 1 fibered, for example, 0, 1 prime times 0, 1 is just E prime fiber times 0, 1. So, and the same thing, well, C times E prime times 0, 1 is the same as C times E prime times 0, 1. So SMU are well defined, and but actually secretly is a special case of the map I already defined, because if I take PR from x times 0, 1 to x, the first projection, then this E prime times 0, 1 is just PR upper star of E prime as a vector bundle. I just mean taking constant along the 0, 1 direction. That's on our side. Okay. Okay. So this lemma is, this proposition, sorry, is secretly saying exactly that the isomorphism classical vector bundles over x times 0, 1 are all pulled back along the projection, which means when you unwrap everything, as in this corollary, that by 0 vect is homotopy invariant. Is it okay? So let me start the proof of this proposition. This is unfortunately rather technical. It goes in various steps. So remember, we have E to x times 0, 1, a vector bundle. And the first step is that we can find the trivialization that are big. So step 1, for each x in X, there exists U neighborhood of x in X, and trivialization of E restricted to U times 0, 1. So if you see x times 0, 1, I can trivialize things in big strips. And okay, how do we do that? Well, for every t in 0, 1, we can find ut, neighborhood of x, and trivialize, and epsilon t, trivialization. Sorry, an epsilon t greater than 0, such that there exists a trivialization on ut times t minus epsilon t plus epsilon. Like, since every neighborhood of x comma t is contains a smaller neighborhood of this form. I can find it like that. And okay, since x times 0, 1 is compact, we can find T1, Tn such that u T1 times T1 minus epsilon T1. Sorry, I forgot that this was epsilon T. T plus epsilon T1, etc. cover x times 0, 1. And okay, now let u to be the intersection and epsilon to be the minimum. As usual, you can always restrict it, it's still going to be a neighborhood. And now we have just a bunch of squares with a trivialization. And so essentially what we have T0 is 0, less than T1, less than Tn, which is 1, and trivialization of E on U times Ti plus 1. But then we can do the trivialization. Inductively. And we obtain trivialization. So you start with the trivialization over 0 to T1, and then this trivialization might be different by an automorphisms on the restriction on x times T1, sorry, on u times T1, but you can use this automorphism to change trivialization. So let me maybe be explicit about how you do it. So let me do the first step. So we have a trivialization. So we have the inverse of u0 T1 is isomorphic to some v times u times 0 T1. And then we have, so let me call this phi 1, and this is called phi 2, T1, T2, v times u times T1, T2. And the v needs to be the same because you can check on a fiber on a point, so say x comma T1. And v, I can take v to be the fiber, x comma T1, for example. Since v is isomorphic to all fibers, I can identify them. Okay, that's great. Now, what do I want to say? Yes. In particular, we get a map, a composition. So you have v times u is isomorphic to v times u times T1. That is isomorphic to the preimage of u times T1 in using phi2 inverse. And then this isomorphic using phi1 to v times u times T1, which is again v times u. And this map is not necessarily the identity, because I have no compatibility of phi1 and phi2. But then, okay, let me call this map F. And then if I take, then I can take F composed with phi2, by which I mean, sorry, F times the identity, composed with phi2 on the last component. And I call this, let's say, phi2 prime. And now I have that phi2 prime restricted to P inverse of u times T1 is equal to phi1 by by construction. Because that's how I built phi2 prime. And so I can glue them together and get phi from P inverse of U times 0 T2 to V times U times 0 T2. It's just, it's the same proof as the unique lifting property for covering spaces, if you remember. Essentially, intervals are easy. You can do one step at a time. And then you can go inductively until you get to Tn. Okay, so this was the easy step. Sorry, this proof is going to be, but okay, to boil down, we have this cone. Oh, no. So we have this step one. We have this cone trivialization, this fat trivialization. So therefore, we can find UI cover of X such that, and trivialization of X E restricted, sorry, to UI times 0, 1. But then by the lemma, we can find Vn countable cover of X and trivialization Vn sorry, Vn, I said. Because as usual, you find this cover such that every element is a disjoint union of subset of some UI, and then you use the trivializations on the UI to build this trivialization here. Okay. Now, let psi n a partition of unity. Subordinate to this cover, and let capital psi n to be just psi 0 plus psi n. So this is a sequence, you start with 0, less than psi 0, less than psi 1, etc. And the supremum is going to be 1.
Do you want the cover to be countable? Have you said that?
I said, sorry, countable cover. I mean, the Vn is the cover given by this lemma. That's why I wanted to be countable, actually. That's what, because I want to do this trick. Okay. Now, okay, here we have this. So what do we want? Remember, we want an iso E prime times 0, 1. And now this is going to be an iso over X times 0, 1. So it's mandated what it's going to do on the second component. So what we want, a map E to E prime over X, which is an iso E x comma t E prime X for every t. and x on fibers. Sorry, I should say it's annoying, but it's not really fibers over x, because you need to take the fibers over x times 0, 1 for E. So that's what we want. And that's what we're going to construct. So we're going to do it inductively on the cover. So we let xn to be x in x such that, sorry, no, not x in x, xt in x times 0, 1, such that t is less or equal than capital phi n of x. I have this thing, it's a closed subspace of 0, 1, and it's in fact, it's a locally finite closed cover of x times 0, 1. It's locally finite because, remember, for any point, only finitely many of the psi n were non-zero, of the lowercase psi n. So psi n, for every point x, is a neighborhood such that psi n is eventually constant on that neighborhood. Is eventually 1. So okay, you can think of it as, you know, take the graphs of this big psi n that tend to 1 in an increasing way, and this cover. So this is xn. It's the area below the graph. And we're going to construct a map Fn from E restricted to Xn into E prime with the above property. For every n. And then use the fact in a compatible way. And then use the fact that if you have a map such that the restriction to every set of a locally finite closed cover is continuous, then the global map is continuous. This is I think it was like the very first exercise I was given in my general topology class, actually, many years ago. But the point is, the idea is I'm going to do one graph at a time. And since this is a partition of unity, in the end, this graph is going to cover everything. So we start with x minus 1. Well, x minus 1 is just x times 0. Since psi minus 1 is 0. So, and here, well, E restricted to x minus 1 is E prime. So we take f minus 1 to be the identity. Okay, good. That was easy. And now suppose we did fn, we need to construct xn. We need to construct the fn plus 1. And here is the point why I introduced this xn. So there are two important properties. So the inclusion xn into xn plus 1 has a retraction. Xn plus 1 into xn over x that fixes the x component. So this sends x comma t to x comma the maximum between psi n of x and the minimum, sorry, like in this graph, I'm just sliding until I hit the next graph. So that's a continuous retraction. And moreover, the other property, which is more important even, is that xn plus 1 minus xn is contained in Vn times 0, 1, where I had a trivialization of my E. Why is that so? Well, because if you have x comma t here, this means that psi n plus 1 of x is greater or equal than t, which is greater than psi n of x. So in particular, this means that little psi n of x is non-zero, because that's the difference. And so x is in Vn by the partitions of unity. Okay. And so, well, we have a trivialization now of E restricted to Vn times 0, which now I realize that my choice of V for the vector space is unfortunate. But I'll, for consistency's sake, I'll keep on it. And so here you can get a map to E restricted to Vn plus 1. This was Vn plus 1. But then, of course, Vn plus 1. So we can get a map E to Vn plus 1 to E restricted to Vn retraction above xn plus 1 to xn. Like, let me call this Rn plus 1. Right, this is a retraction above a retraction that I had. It's just applying the retraction on the second component and the identity on the first component. And therefore, I can glue it together with the identity and get a retraction of E restricted to xn plus 1 to E restricted to xn. Actually, I'm going to call this also Rn plus 1. And then we let Fn plus 1 to be the composite. E restricted to xn plus 1 goes to E restricted to xn, goes to E prime with Fn. And we are done. And this was the end of the proof of homotopy invariance. Sorry if it was more technical. The next one is going to be easier, the next important lemma, and then we're going to go back to do homotopical stuff. Questions about this proof? It's a bit magic, but if you try to write it down, you see that you're just doing, well, okay. It's still going to look magic even after you've wrote it from themselves, but it's hopefully going to be more understandable. I don't know how people invent these proofs, honestly, but some people seem to be able to. Okay, the following lemma is a lot easier, thankfully. The following lemma is, so suppose that P from E to X vector bundle and X as usual paracompact Hausdorff. Then there exists a map from E to C infinity, C linear in each fiber, C linear and injective, sorry, on each fiber. And actually, maybe I should say what I mean by C infinity. C infinity is the union of Cn for every n, that is the sequences sorry, C to the n, such that xn is 0 for almost all n. I don't know if you've seen this space before. It's a C vector, it's just a C vector space with a countable basis. But this way I'm actually telling you what the topology is the inductive limit topology on this union. And technically you should think of it as an int vector space or whatever, but I'm not going to play these kind of games. Think of it like a topological vector space. It's not complete, very far from complete, of course, but I don't care. Okay, and this is saying every vector bundle can be embedding. You can find in a sense, this is telling you that you can find a continuous embedding of every fiber into C infinity in a way that varies continuously on X. And moreover, if X is compact, we can find F from E to some finite stage. So things for which only the first n components are non-zero. In fact, this proof is very, very easy. So the idea, let un be a countable trivialization of E. Then for every n, we have in particular maps from E restricted to un into C to some dn. It's not very important. It's probably going, in general, it's going to be like probably constant, but you know, if X has various connected components, the rank can vary, can jump from connected component to connected component. Sorry, I should say ISO on each fiber of E. It's just the projection of the trivialization. Okay, let psi n partition of unity, as usual. And then the map F from X to C infinity is exactly what you would think it is. It's this map F of E is psi 0 P of E times, oh, sorry, let me call them Fn. F0 of E, psi 1 P of E times F1 of E, etc. in C of D0 plus D1 plus etc. that is in C infinity. And these make sense because it's true that Fi is defined only in UI, but outside of UI, this guy is 0. So I'm taking just the 0. I'm extending by 0 this continuous map. So this actually makes sense. And for every E, only finitely many of these are non-zero. So this actually lands into C infinity. And for every E, one of these components is an ISO on the fiber, because this number is non-zero. And if X is compact, I can just choose finitely many UNs. And this gives me the finiteness statement I was looking for. Okay? So this is a very explicit construction. Questions about this? And this is the general statements about vector bundles I wanted to say. And now I think I have 40 minutes. It should be enough to do at least the first half of the proof of the theorem. And then we'll see how much time do we have. Otherwise, we're going to finish it on Thursday. Questions about this? So remember, we have these two statements. First, that vector bundles are homotopy invariant. And second, that vector bundles, as I say, have complements in some sense. You can embed them into constant vector bundles in some level. So for example, when X is compact, this gives you an embedding, of vector bundles into a trivial vector bundle. And that's also the same when X is not compact. That's how you should think of it. It's just that a finite dimensional vector bundle might not be enough. So you have this X times C infinity. And let me give you an exercise. So if Z into X is a cofibration, you can choose F as above, agreeing with a given F0 from E restricted to Z. So if you have a cofibration, remember it's a closed cofibration, I should say. But we are in paracompact Hausdorff spaces, so I think all cofibrations are always closed in Hausdorff spaces. So if you have a closed subset, a sufficiently nice closed subset, you can ask this F to agree with something. We're not going to use this, but I think it's an exercise to understand a little bit how this proof works. Okay. So, okay. Now let M infinity C as a subspace of the product of N times NC be the space of C linear maps from C infinity to C infinity. So a C linear map is represented by some big matrix, as usual. And they're not all the matrices. Technically, you need all the columns to have only finitely non-zero entries. Otherwise, the image of an element in C infinity is not necessarily in C infinity. You need the sums to be finite. But I'm topologizing it. If you want, another way of saying it is that you can topologize it as the limit. Well, no, I'm not going to be more precise, actually. And you can compose them, and you have, for example, for every A in M infinity C, you can have a notion of conjugate transpose, as usual. Just transpose it. This actually works only if A has finitely many non-zero horizontal entries. Every row has finitely many non-zero entries, but I'm going to write A transpose conjugate only in the case in which A is actually not always, but we'll write it. We'll write it only in this case. And okay, now it's time for the definition of the object that's going to be the important part, which is the d-dimensional Grassmannian. That's the space of all P in M infinity C, such that the rank of P, I mean the dimension of its image, it's D, it's finite and it's D. P square is P, is a projection, and it's an orthogonal projection. So maybe, I'm not sure if you remember it from when you did linear algebra. Every vector subspace always has an orthogonal projection, and the rank of the orthogonal projection is equivalent to the thing. And in fact, this is also the trace of the orthogonal projection, because orthogonal projections have eigenvalues only 0 and 1. So the trace is exactly the same as the rank. But okay, that's a minor point, just to show that the rank is a continuous function on these matrices, because it's a restriction of the trace. Okay, and we think of it this as the space of v-dimensional subspaces of C infinity, since there is a bijection between the points of this space and d-dimensional subspaces of C infinity. And I'm going to give you an exercise to understand a little bit how this works. So let V in GRD, I mean a d-dimensional subspace, i.e. a d-dimensional subspace of C infinity. We have a map from the C-linear homomorphism from V to V orthogonal into GRD that sends F to the graph of F in V plus V orthogonal C infinity. That is the subspace of the subspace here, which is also d-dimensional subspace. And okay, that's I have a map. I just defined it for you. It's a map of sets. And the claim is show that this is an open embedding with image those W in GRD such that the projection is surjective. The orthogonal projection is surjective from W to V. And this description is actually, the description tells you that this subset is open, because if you write it in terms of projections, this is saying the trace of PV, PW is D. And that's an open condition. No, sorry, the rank, I should say. Well, greater or equal than D, really, but okay. And that's an open condition. That's the non-vanishing of a bunch of determinants. So this tells you that this subset is open. You just need to show that it's a homeomorphism with this subset here. And that's going to be useful. That's called the standard charts in the Grassmannian. And I'll let you to do the exercise of finding the inverse of this map. It's less hard than you would think. But we're going to use it because we're going to need to show that a bunch of stuff is a fiber bundle over the Grassmannian, and they're going to be trivialized by these open subsets. Is this exercise clear? Okay, good. This Grassmannian secretly will be a model for BUD, by the way. That's why I'm introducing it. A geometric model for BUD. But that proof, I don't think we're going to get to that proof later. But we can do the first part. So we have, so definition, the tautological bundle psi d over the d-dimensional Grassmannian is the space psi d in C infinity times the Grassmannian. So given by V comma V, such that V is in V. Or if you want to think in terms of P of the projections, which is how I topologized, I have this conditional here. That's what it means to lay in the subspace. So it's actually a well-defined closed subscheme of the closed subspace of this C infinity times GRT. So okay, and why did I call it a tautological bundle? Well, because it is a vector bundle. This is a vector bundle trivialized by the standard basis. And it's tautological because the fiber over V is exactly V. And in fact, you can see that psi d restricted to hom V the orthogonal in the standard basis is V times hom V the orthogonal. And the vector space structure on the fiber is given just by acting on this component, just by summing and multiplying by scalar on this component. You can see that this is, you have df, you go to, graph of f comma f of v. Sorry, v comma f of v. This gives you a bijection. And now, I hope I'll have the time to prove this theorem. Well, we'll see. Is the definition of a tautological bundle clear? It's just a bundle that to every point on the Grassmannian, the fiber above is the vector space corresponding to that point. That's why it's called the tautological bundle. And the theorem is that the map from homotopy classes of maps into the Grassmannian to pi0 vect x, sending f to the pullback of psi d, is a bijection. So you can think, if you have a vector bundle, somehow this map from x to the Grassmannian, you can think of it as sending every point to the fiber over that point, morally. Let's see how this goes. So first, this is well defined because pullbacks are homotopy invariants. So find by homotopy invariance. And now, okay. Now the question is, what does it mean to give? So let E to X be a vector bundle. Ooh, sorry, vector bundles of rank D, of course. You can only get vector bundles of rank D in this way, right? Because psi D is a vector bundle of ranks D by construction. So, yeah.
For the first sentence, you use something, right? Maybe that the vector bundle is always a vibration or something like that.
No. I'm using that the pullback of a vector bundle is a vector bundle.
Yeah, but for homotopy invariance.
So sorry, when I mean homotopy invariance, I mean that pi0, that if F and G are homotopic, this means that F upper star of psi D is homotopy equivalent to G upper star of psi D. Sorry, not homotopy equivalent, it's isomorphic, which is the result that the first result we proved today. Remember, let me go back to where we did. Okay, this was the very technical proof that we used, but we have this corollary. So we have two maps that are homotopic. We want to show that the pullback of the same vector bundle are isomorphic. So that's what I mean by homotopy invariance, and that's what I mean that the map is well defined by homotopy invariance. Okay? Okay, so now we have a vector bundle. So what does it mean to give a map, to give an isomorphism like this? Well, remember, phi upper star psi d is exactly this fiber product. So certainly giving a map from E to F upper star psi d. So a map E to F upper star psi d is a map like this. And to say it's an isomorphism, it means that phi is an isomorphism on every fiber. And remember, this is a subspace here. So giving phi is the same as giving, say, f tilde from E to C infinity, such that f tilde of Ex of the fiber, the image of the fiber over Ex, is exactly the subspace f of x. And sorry, and phi tilde is injective, because we don't want to lose rank. So note that this in particular tells you that f tilde determines f. So a pair f and E psi d is the same thing as a map f tilde from E to C infinity, which is a C-linear embedding on each fiber. But wait a second. Didn't we just prove that for every vector bundle there is one of those? We did, right? So in particular, this map x grd to pi 0 vect x is surjective. Okay, that's great. We only have to do injectivity and then we're done. I just wish injectivity were simple. It's not too complicated. And using the same reasoning, this boils down injectivity boils down to show that if we have f tilde g tilde any map, which is an embedding on each fiber, then they are homotopic. And in fact, this is a consequence of that exercise I gave you, although I'll give you a different proof here, but I'll just show you how this exercise works. You could deduce it, you could see this as extending a map from E times the border of the one simplex to E times the one simplex. right? This map from E to the border of one simplex is just a pair of maps, which are F tilde and G tilde. So this is going to be my, so X times the border is going to be my Z, and this is going to be in X times delta 1. So this actually follows from the exercise I gave you. But I'm going to give you a different proof, an explicit proof here. So, okay, so we have F tilde and G tilde, and we want to show that they are homotopic. So first of all, we have a homotopy 0, 1 times C infinity into C infinity, sending T comma X dot to T x0, x1, etc. plus 1 minus T x0, 0, x1, 0, etc. You have this homotopy that's moving everything to the even numbered coordinates. And it's a homotopy through embeddings. You can check that this map is an embedding, a linear embedding for every T. It's injective for every T. That I'll leave you as an exercise to use. Sorry, it's really not hard. And we also have, so that we have this, and we also have this X prime, H prime. Which is its little brother that moves you in the odd dimensional coordinates. The odd number coordinates. Okay. So by taking H F tilde and H prime G tilde, we can assume F has values only on the even numbered coordinates. Sorry, F tilde. And G tilde has values only on the odd numbered coordinates. Right? I can homotopy them through embeddings. Okay, but then T F tilde plus 1 minus T G tilde is the homotopy we're looking for. Because it's going to be injective for every T, since F tilde and G tilde do not speak to each other. And that actually ends the proof of the representability result. I went a little faster than perhaps I thought. I might be able to even prove the homotopy equivalence of GRD with BUD, but other questions about this proof? And okay, let me do a small, yes?
So did we ever use the property of GRD that the complex conjugate transpose for P is P again? And
it's just to get a bijection between projections and vector subspaces.
Ah, so we use this.
I am secretly thinking of GRD as the set of all subspaces of rank D of C infinity, and just using the projection description to give you a topology on that set.
Okay.
And you actually should check that a bunch of maps that I told you to be continuous actually are continuous, but with the projection description is very, very easy. That's why I've chosen it, and that's why I'm sort of skipping through it. You can just unwrap what it means and see that it does. So okay, so we have pi 0 vect dx is the same thing as homotopy classes of maps from X to GRD. And in fact, the level of an excess, well, it's not really an exercise, it's more a remark, but vect X is homotopy classes of maps from X to the disjoint union of GRD. That's because in each connected component, a vector bundle has a well-defined rank, since the rank is locally constant. And so, and you know that every map like these factors through one of these summands on one connected component. And each connected component it factors. Okay. Good. Okay. The next thing I want to say, so the next theorem I want to say is GRD is actually equivalent to BUD. Or pretty much equivalently, the loop space of GRD is EUD as an E1 group. It's multiplication given by the multiplication of matrices. Okay, technically you have to show that GRD is connected for this to be true, and choose a base point, but okay. That's going to be the easier part, show that GRD is connected. The important part. Yes. So to do that, I'm going to use a lemma that is very useful, and in fact, it proves a more general version of this result I'm talking about. So let G be a topological group, and I think I'm going to prove only this lemma, and then I'll show the application of this lemma. P from E to be a fibration with E contractible. And assume G acts on E over B, by which I mean that every element of G is a map from E to E over B. It preserves the projection on B, i.e. this commute, and that the action is simply transitive on each fiber, by which I mean something slightly stronger than literally the action is simply transitive on each fiber. I mean that the map G times E to the fiber product given by this GE comma E is a homeomorphism. In fact, you need less than this, but let me ask for this stronger condition. Then there exists homotopy equivalence, of E1 spaces G and loop space for any point. Oh, sorry, I should say surjective fibration. Otherwise, it won't work. When B is any point. I mean, I just need any point on the image of B, really. mean, I'm just this surjectivity condition is just B might have some connected component that receives no element of E, and that's crap. We don't want that. So one thing, the first thing is to notice that if we wanted only an equivalence of spaces, it would be easy. Because G is equivalent to the fiber over EB just by picking E on this fiber and taking the map G to EB. G goes to GE, which is an equivalence because it's an equivalence on the fiber over E of the projection to E, on the second projection to E here. It's actually a homeomorphism. And so you have a pullback square pullback in top, but it's a homotopy pullback because P is a fibration. That's exactly the only reason why we want P to be a fibration. So G is equivalent to the loop space since E is contractible. And this is equivalent for point. And the proof that it's a map of E1 spaces is essentially the same proof, only done more carefully. But it's clear, is this proof clear? Okay, and okay, so now let's do the proof in the general case, checking that the group structure is also the same. So that multiplication in G corresponds to concatenation of loops. And the point is that I defined this guy here as, you remember, the limit of this diagram. And I can also write it actually as this fiber product. I think we discussed at some point that this is the same as this iterated fiber product. And this is our homotopy pullbacks. In this definition, of course, strict pullbacks will be just a point. And then, since E is contractible and P is a fibration, it's this simplicial space here. But now, by induction, using G times E is equivalent to this fiber product, we see that omega B n is going to be G times G times G n times E. And E was contractible, remember? And that's G times G. And actually, you have to check that the maps are the same as the maps that I'm claiming you, but everything is explicit. So this is, remember, this is just G brackets n. When you identify G, you know, commutative monoid in the classical sense with this coherent notion of commutative monoid. And you actually have to check that this is natural in n. I haven't technically spelled it out, but all the maps are completely explicit. So you can see that the maps are indeed the same maps for G and for omega B. Okay. Oh, and when I say fibration, sorry, throughout I mean self fibration. But okay, we're working basically with CW complexes, so there is no difference. If you remember, there was some difference in the general case that I'm going to happily ignore for now. Yeah. And also in the following. Okay, is this proof clear? It's essentially the same proof as the proof at the level of spaces, just done carefully for every n, and see what happens. So I'll be embarrassed. I had to ask someone to help me find this proof because I knew it existed. I just couldn't reconstruct it on my own. So if it seems magic, don't be too surprised. And okay, I don't think I have the time, but I just say, okay, next time we'll construct a fiber bundle VB over GRD and a UD action on VB that satisfies the hypothesis dilemma. And this is, if you've ever seen it before, this is going to be the Stiefel manifold. The infinite Stiefel manifold, which is not a manifold anymore, actually, but it's more like in manifold. But like you take a union of manifolds of bigger and bigger dimension until you get this thing. And yeah, I don't think I can reasonably give you the proof. I mean, I can give you the definition of VD actually. That's kind of easy. VD is just the space of embeddings of CD in C infinity. And it has a map to GRD, sending an embedding to its image. Sorry, I mean isometric embeddings. And if you want to take the projection model to see that this map is actually continuous, this is just saying F, sending F to FH times F. No, sorry, F times FH-ish. Okay, that's always, well, whichever goes from C infinity to C infinity, because you want a projection. So you see that indeed this map is obviously continuous. That's why I like the projection model, because it allows you always to do these things in a very simple way. But that's of course now how you think. I mean, you think of this map as sending F to its image. And okay, and this turns out indeed to be contractible. And the action by UD, actually, at this point I could tell you, the action UD is by precomposition. And you can indeed check that it satisfies all the hypotheses on the lemma very easily. But okay, you need to prove that VD is contractible, which is slightly long, so I'll leave it for next time. Okay. And maybe you've seen this contractibility statement already, because in the case when D is 1, V1 is just S infinity, the unit sphere in C infinity, because it's determined only by the value of the first basis vector. The image of the first basis vector determines the isometric embedding. And maybe you've seen this already, that this is, I think we might have discussed it last semester. I'm not sure if I remember it, maybe not. But okay. Anyway, this unit sphere is contractible. And it's going to be a consequence. It's going to be needed to do one of the exercises that I put on this morning. You can take it for granted. I'm going to prove it on Thursday anyway, that this thing is contractible. So, if you've never seen it before. Okay, I think that's all I have.
maybe is there a connection between the fact that fiber bundles are vibration for paracompact Hausdorff spaces and the homotopy invariance of vector
Yes,
bundles?
I mean, to be precise, the connection is this lemma I skipped here. This lemma that you can find for any covering. The general theorem says that if you have a countable fiber bundle over any space, then it is a Serre vibration. Sorry, then it's a Hurewitz vibration. Countable, I mean a fiber bundle that has a countable trivialization. And use this lemma to reduce to that case. And yeah, the argument for this theorem that I'm claiming is not that different from the homotopy invariance. It's one of those things where you have to. Now, I don't remember the details, but essentially you use the fact that you can lift stuff on trivialized things, and you build it inductively, and you use the countability to do an induction argument. That's the point. As I did it for constructing this trivialization here, where was it? Here, this xn. You do the countability to do an induction in the building like a lift. In this case, you have to prove a homotopy lifting property, right? So you have to prove a lift on bigger and bigger things. Induction. And that's the kind of arguments that appear right now. If you ask me the details, I'm unprepared. I don't remember the details of that proof, but it's the flavor of the argument is not that different. I guess that's the point.
But there is not a way to use the statement about vibrations to prove this statement.
No,
here, you know?
There is a more general statement that tells you that for any sufficiently nice topological group G, G torsors, or what are called principal G bundles, are homotopy invariant, which I think Pavel is going to give us an example on Wednesday. And that's actually the general statement that that is going to be interesting. But okay, I didn't want to define a principal G bundle and prove that principal UN bundles are the same thing as vector bundles and etc. because just in the interest of time. But of course, there is a bigger story behind this. It's typically done often in differential geometry classes, I think, these kind of arguments, because they're used to build connections on bundles and stuff like that. But of course, it's interesting also for other reasons. I don't know when people are supposed to learn about vector bundles, by the way. I think at some point people are expected to know what they are and how they behave, but it's not clear to me in which class. You're right, probably differential geometries, they're often mentioned because you need a tangent bundle. So I don't think they're going to prove, I don't think it's usual to prove this theorem here. Which is a very important theorem on some level. I wish I had time to talk about characteristic classes, but which are studied by this theorem, but I don't. I'm just going to be able to introduce topological K theory, which I'm going to do next time. Okay, other questions? If not, I'll stop the recording.